Imagine everything you've ever known, every atom, star, planet, and galaxy compressed into a single, infinitesimally small point. Everything that exists, everything that has ever existed, and everything that will ever exist, all contained in a space smaller than the smallest particle we can conceive. Then, in an instant, it all explodes outward. Time begins. Space unfolds. The universe is born. This is the story we've been told. The Big Bang as the ultimate beginning. The moment when literally everything started. But here's the question that keeps cosmologists awake at night. Is this the whole story? Because if we rewind the cosmic clock back to that first moment, before the first second ticked by, before energy cooled into matter, before even the laws of physics existed as we understand them, what was there? Was it truly nothing? A quantum vacuum seething with invisible potential? A collapsing universe from a previous cycle? A collision of higher dimensional membranes we can barely comprehend? Or something we don't even have the words for yet? Today, we're going to dig into some of the most mind-bending ideas in modern cosmology and approach the very limits of what science, and maybe even thought itself, can reach. Welcome to the ultimate question. What came before the beginning? The Big Bang, what we know. Let's start with what we're relatively certain about. And I say relatively because even our most well-established theories come with caveats. The Big Bang theory tells us that approximately 13.8 billion years ago, the universe began in an incredibly hot, dense state and has been expanding ever since. This isn't just speculation. We have mountains of evidence supporting this model. First, there's cosmic expansion. In the 1920 seconds, Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This suggests that space itself is expanding, like dots on the surface of an inflating balloon. If everything is moving apart now, then logically, everything must have been closer together in the past. Then there's the cosmic microwave background radiation, the CMB. This is the afterglow of the Big Bang itself, a faint whisper of light that fills the entire universe. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, this radiation is exactly what we'd expect to find if the universe started in a hot, dense state and has been cooling ever since. We also see the predicted abundances of light elements, hydrogen, helium, and lithium, formed in the first few minutes after the Big Bang through a process called Big Bang nucleosynthesis. The ratios match our predictions with stunning precision. But here's where things get tricky. The Big Bang theory describes what happened from a fraction of a second after the initial event onward. It tells us about the expansion, the cooling, the formation of matter, and eventually atoms, stars, and galaxies. But it hits a wall when we try to go back to the very beginning, to time zero itself. At that point, our equations break down. Density becomes infinite. Temperature becomes infinite. The very fabric of space-time becomes so warped that our current physics simply can't describe it. We call this a singularity, not just a point in space, but a boundary where the laws of physics cease to function. So when we ask what came before the Big Bang, we're not just asking about a time period. We're asking whether the question itself even makes sense. The problem with before. Here's where we need to address something fundamental. What does before even mean? We're so used to thinking in terms of cause and effect, of one thing following another in time, that it's almost impossible to think any other way. But according to general relativity, Einstein's theory of gravity and spacetime, time itself came into existence with the Big Bang. Think about that for a moment. Time isn't just a backdrop against which events unfold. Time is part of the universe. It's woven together with space in what we call space-time. If space-time itself was created in the Big Bang, then asking what came before is like asking what's north of the North Pole. The question doesn't make sense because you've reached the boundary of where that dimension applies. This was the position of Stephen Hawking and many other physicists. In Hawking's own words, asking what came before the Big Bang is like asking what lies south of the South Pole. It's a meaningless question because time itself began at the Big Bang. But not everyone is satisfied with this answer, because while it's philosophically consistent, it doesn't explain why the Big Bang happened in the first place. It doesn't explain why there's something rather than nothing. And it certainly doesn't quell our very human desire to understand the ultimate origin of everything. So scientists have developed several theories that attempt to extend our understanding beyond that initial moment. Some of these theories suggest that the Big Bang wasn't the absolute beginning, but rather a transition, a phase change in something that already existed. Let's explore these ideas, starting with one of the strangest. The concept that the universe came from nothing. Something from nothing, the quantum vacuum. When most people hear nothing, they think of absolute emptiness, the complete absence of anything. But in quantum physics, nothing is far more interesting than that. In quantum field theory, even empty space, what we call the vacuum, is never truly empty. It's seething with activity. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum itself for impossibly brief moments before annihilating each other. This isn't science fiction. It's been experimentally verified through phenomena like the Casimir effect. So here's the radical idea. What if the entire universe is just a quantum fluctuation that got out of hand? The physicist Edward Tryon proposed this in 1973. Suggesting that the universe might be a vacuum fluctuation of enormous scale. Normally, these quantum fluctuations are tiny and short-lived. But under the right conditions, and we're talking about conditions that are barely comprehensible, a fluctuation could become macroscopic and last indefinitely. Here's where it gets even stranger. The total energy of the universe might actually be zero. How? Because while matter and radiation have positive energy, gravity has negative energy. When you do the math, and this is highly simplified, they might perfectly cancel each other out. If the universe has zero total energy, then its creation wouldn't violate the law of energy conservation. It would be the ultimate free lunch. But this raises immediate questions. If the universe can spontaneously emerge from quantum fluctuations, why did it happen 13.8 billion years ago? And not earlier or later? And what is this quantum vacuum fluctuating in? Does it require some kind of pre-existing quantum field or space? Some physicists, like Lawrence Krauss, have argued that the laws of quantum mechanics themselves might be all that's needed, that these laws could exist without a universe for them to operate in. But this pushes the question back one level. Where do the laws of quantum mechanics come from? Others point out that this quantum vacuum isn't really nothing. It's a highly structured something with specific properties and laws. So we haven't really explained the ultimate origin. We've just moved the mystery one step back. Nevertheless, the quantum vacuum hypothesis remains one of the most scientifically grounded attempts to explain how the universe could emerge from nothing, even if that nothing is a very special kind of something. The eternal cycle. X. Bouncing universes. What if the Big Bang wasn't the beginning at all, but just the latest in an infinite series of cosmic cycles? This idea has ancient roots. Hindu cosmology has long described a universe that cycles through creation and destruction, but modern physics has given it new life with what we call cyclic or oscillating universe models. The basic concept is this. The universe expands from a Big Bang, eventually stops expanding, and then collapses back in on itself in a big crunch. But instead of ending in a singularity, something happens at that moment of maximum compression. Perhaps quantum effects dominate, and the universe bounces back, triggering a new Big Bang. This cycle could repeat eternally, with each universe lasting trillions of years before collapsing and rebirthing. There would be no absolute beginning and no absolute end, just an infinite series of cosmic incarnations. One version of this is the Cyclic Universe Model, developed by physicists, including Paul Steinhardt and Neil Turok. In their model, the Big Bang was the result of two three-dimensional membranes, branes for short, colliding in a higher dimensional space. This collision released enormous energy, which we experience as the Big Bang. The branes then separate, eventually colliding again in a new cycle. These models have some attractive features. They avoid the singularity problem, the moment when physics breaks down because the universe never actually reaches infinite density. They also provide a natural explanation for why the universe is so flat and uniform, which otherwise requires a special initial condition or the theory of cosmic inflation, which we'll discuss shortly. But cyclic models have their challenges too. For one thing, the second law of thermodynamics, which states that entropy, or disorder, always increases, poses a problem. Each cycle should become more disordered than the last, eventually leading to a heat death where no useful energy remains. How can the universe reset itself and maintain its order through infinite cycles? Some cyclic models propose mechanisms to reset entropy at each bounce, but these remain controversial and not fully worked out. There's also the question of what determines the properties of each cycle. Are they the same each time, or do the laws of physics change from one universe to the next? And if they change, what meta-laws govern those changes? Despite these challenges, cyclic universe models remind us that the Big Bang might not be the ultimate beginning. Perhaps we exist in an eternal cosmic drama with no first act, colliding branes. The multiverse in higher dimensions. Now let's venture into even stranger territory. The idea that our universe is just one of many, existing in a higher dimensional space we can barely conceive. This concept comes from string theory, which attempts to unify quantum mechanics and general relativity by proposing that the fundamental constituents of reality aren't point particles, but tiny vibrating strings of energy. Different vibration patterns of these strings correspond to different particles, electrons, quarks, photons, and so on. But here's the catch. For the mathematics of string theory to work, it requires extra dimensions beyond the 3 dimensions of space and one of time that we experience. Depending on the version, string theory requires 10 or 11 total dimensions. Where are these extra dimensions? The usual answer is that they're compactified, curled up so small that we can't detect them directly. But some versions of string theory, particularly M theory, suggest that our entire universe might be a 3-dimensional membrane, a brane floating in a higher dimensional space, called the bulk. Now, imagine that there are multiple branes in this bulk, each potentially containing its own universe with its own laws of physics. Our observable universe would be everything that exists on our particular brane. According to the ekpyrotic model I mentioned earlier, these branes can collide. When our brane collided with another, the enormous energy released manifested as the Big Bang. From our perspective, trapped on our 3-dimensional brane, it would look like the universe suddenly exploded into existence. But from a higher dimensional perspective, it was just 2 branes bumping into each other. This model explains several puzzling features of our universe. It accounts for the uniformity of the cosmic microwave background. The collision would naturally spread energy evenly across the brane. It also provides an alternative to cosmic inflation, which I'll discuss shortly. But brane cosmology raises as many questions as it answers. What exists in the bulk between branes? What determines when branes collide? Are there countless other branes out there, each with their own universes? And if so, how different are they from ours? We're now firmly in the territory where observation becomes extremely difficult. We can't directly detect extra dimensions or other branes, at least not yet. The best we can do is look for indirect signatures in the cosmic microwave background or in gravitational waves, and hope that these phenomena might give us clues about higher dimensional physics. Inflation and the multiverse. Let me introduce you to one of the most important and bizarre ideas in modern cosmology: cosmic inflation. In the 1980 seconds, physicists, including Alan Guth, realized that the standard Big Bang theory had some problems. The universe is remarkably uniform. The temperature of the cosmic microwave background is nearly identical in all directions, varying by only about 1 part in 100,000. But if different regions of the early universe were never in contact with each other, never had time for light to travel between them, how did they all end up at the same temperature? This is called the horizon problem, and inflation solves it elegantly. The theory proposes that in the first tiny fraction of a second after the Big Bang, we're talking about 10 to the minus 36 seconds, the universe underwent an incredibly rapid expansion, growing exponentially in size. During this inflationary period, a tiny patch of space, small enough that all parts of it were in causal contact, expanded to become larger than our observable universe. This explains the uniformity we see. Different regions of the observable universe look similar because they all came from the same tiny, uniform patch before inflation stretched it out. But here's where things get wild. In many versions of inflation, called eternal inflation, the inflationary process doesn't stop everywhere at once. While inflation ended in some regions, including our observable universe, it continues in other regions, spawning new bubble universes continuously. Each of these bubble universes could have different properties, different constants of nature, even different laws of physics. Some might be hospitable to life. Most would probably be sterile and lifeless. But together, they would form a vast multiverse, an infinite ensemble of universes, each with its own history and characteristics. In this picture, the Big Bang wasn't the creation of everything. It was just the moment when inflation ended in our particular bubble. The inflationary field continues to exist outside our bubble, constantly creating new universes in an eternal, ongoing process. This has profound implications. If there are infinite universes with different properties, then it's not surprising that we find ourselves in one that's suitable for life we couldn't exist in any of the others. This is an application of what's called the anthropic principle. The universe appears fine-tuned for life, because if it weren't, we wouldn't be here to observe it. But the multiverse concept is controversial. Critics argue that if we can never observe or interact with these other universes, the multiverse isn't really a scientific theory. It's not falsifiable or testable in the way that science requires. Proponents counter that the multiverse is a prediction of inflation, which is testable, and that we shouldn't reject a theory's predictions just because they're philosophically uncomfortable. The debate continues, but one thing is clear. If eternal inflation is correct, the Big Bang was far from the beginning of everything. It was just a local event in an infinitely larger and older cosmic landscape. The Hartle-Hawking no-boundary proposal. Stephen Hawking, working with James Hartle, proposed one of the most elegant and mind-bending solutions to the question of what came before the Big Bang. Nothing came before it, because there was no before. Their no-boundary proposal uses a mathematical technique called imaginary time. Now, I know that sounds like science fiction, but bear with me. In physics, imaginary numbers involving the square root of -1, are perfectly legitimate mathematical tools. Hawking and Hartle proposed that in the earliest moments of the universe, time had a different character than it does now. Near the Big Bang, time behaved more like another dimension of space. The distinction between time and space became blurred. Here's the crucial insight. If you model the universe this way, using imaginary time, the universe has no boundary in time. It's finite but boundless, like the surface of a sphere. Just as a sphere has finite area but no edge, you can travel around it forever without hitting a boundary. The universe is finite in imaginary time, but has no temporal beginning or end. When Hawking was asked what came before the Big Bang, He famously replied that the question has no meaning. It's like asking, what's north of the North Pole? Time itself begins at the Big Bang, but not in a way that creates a singularity or requires a before. In this model, the universe didn't come from something, nor did it come from nothing. It simply exists as a self-contained, four-dimensional object in space-time. No creation event, no first cause, no moment of beginning. The universe just is. This is philosophically profound, but incredibly abstract. It requires thinking in imaginary time, which has no direct physical interpretation. And like many ideas we've discussed, it's extremely difficult to test experimentally. But the elegance of the no-boundary proposal has captivated many physicists. It provides a complete description of the universe that doesn't require anything outside the universe to explain it. In Hawking's own words, what place then, for a creator, the limits of knowledge? As we've journeyed through these mind-bending theories, you might have noticed a pattern. Each explanation either pushes the mystery back one step or requires us to fundamentally rethink our concepts of time, causation, and existence itself. This raises a profound question. Are we approaching the limits of what science can tell us? Are there some questions that, by their very nature, might be unanswerable? There are several reasons why the question, what came before the Big Bang, might be uniquely challenging or even impossible to answer definitively. First, there's the observational barrier. We can only observe our universe from the inside. If something existed before the Big Bang, or if other universes exist beyond ours, we might have no way to detect them directly. The cosmic microwave background forms a kind of cosmic horizon. We can't see beyond it to earlier times, just as you can't see beyond your horizon on Earth. Second, there's the mathematical breakdown. Our current theories of physics, quantum mechanics, and general relativity work brilliantly in their respective domains, but can't be reconciled with each other. At the extreme conditions near the Big Bang, where both quantum effects and gravity are important, we need a theory of quantum gravity. Despite decades of work on string theory, loop quantum gravity, and other approaches, we don't yet have a complete, tested theory. Third, there's the conceptual challenge. Our brains evolved to understand medium-sized objects, moving at medium speeds the world of our everyday experience.